This is Apollo Control at 1:60 hours 24 minutes. Switching now to Air Ground 1 for the initial wake-up call to the crew of Challenger. Asleep at this time at Carlos Littrow. We'll stand by for the wake-up call.
Hello there, Challenger. The Gold Team flight director picked out the morning selection, and he said that if you can find some maroon dirt today instead of orange, you'll probably get a lot more cooperation out of him.
I figured the Gold Team might do that. You know, I woke up to a lot of pleasant thoughts, never to an Aggie before.
Greetings, Earthlings! Tonight we are howdy howling at the moon. A whoop! We're here for International Observe the Moon Night 2024. Smash hits and glorious glasses. I'm Dr. Allison McGraw, but you can call me Dr. A. I manage the Physics Lab Center at the Physics and Astronomy Department here at beautiful Texas A&M University. Tonight we're going to you live from the Simpson Drill Field at the main campus here in College Station. Tonight, our focus is the biggest impact physics on the moon. The largest drivers of our solar system are indeed planetary impact physics. And hey, we're just along for the ride. We'll take a tour tonight showing you some of the largest impact basins. We've got images through our telescopes to show you. We've also got a curated sample returned from Apollo 15 on loan from none other than our beloved NASA. We have our NASA Moon Tree, which is also going to be revealed for the winner of the naming competition near the end of the live stream tonight. Our NASA Moon Tree flew on Artemis 1 mission in orbit around the moon in the fall of 2022. We will be also broadcasting throughout the live stream, and at the beginning, I hope you enjoyed the Moon's Symphony, excerpts from that, as well as our war hymn that was broadcasted to the Apollo 17 astronauts on the surface of the moon in the year 1972. We're happy that this is also a small hint to give you who might have won our NASA Moon Tree competition. So let's go ahead and dive on into what we will look at tonight. This is brought to you by International Observe the Moon Night. This is a global moon party, y'all. Everyone around the globe is encouraged to look at the surface of the moon through whether it's telescopes with your human eye, binoculars. This was inspired by NASA's return of the first highest resolution images of the moon. We're talking about resolving about the things the size of my desk here, folk, on the surface of the moon from orbit, from the Lunar Reconnaissance Orbiter Camera, or LROC. NASA scientists were so inspired when those first images came down, they said, hey, we should throw a moon party. So here we are, throwing our iteration of our International Observe the Moon Night. So let's go ahead and kick it to our International Observe the Moon Night viewer. We're going to take a look at the mare, the lunar mare. Okay, so this is one of the first features that you see when you look visually at the surface of the moon. These are some of the oldest and largest impact basins. In fact, these impacts on the moon were so large, they become lava filled. So the dark mare, the lunar mare that you see, are infilled lava basins from huge impacts that struck when the moon was very young. We're talking over 300 billion years ago, folk, at the time when there was still a molten mantle for that lava to rise up from the mantle of the moon and infill those basins. This is called the Sea of Rains for this mare region here. From edge to edge, this is like the distance from New York down to Louisville, Kentucky. Now we also have, of course, a different type of crater, Tycho crater. Tycho crater is also one of the most identifying objects when you look both with your eye or with binoculars. This is in that southern part of the moon region, the southern hemisphere. This is spectacular. This is 53 miles wide. This is 3 miles deep, just to give you a sense of that scale. And this is what we call a complex crater, y'all. Complex craters have a little bit more going on. Notice that there's a lump in the center. This is the same physics as when you drop a big bowling ball into some water and that water gushes up towards the point in which it actually impacted from. This is the same happening with the central pit inside this complex crater, although it's now with rocks and excavated material that once was the bedrock, which rises up, collapses on itself, and shoots out large ejecta blankets that you can see. They radiate almost a section that you can see. Now our last is where our Apollo 15 sample collected. Now this was the 4th crewed mission that NASA brought to the surface of the moon, and it was the first time that we actually got to take a little joyride on the moon with that lunar rover, or lovingly called the jalopy. All right, so driving the jalopy on the surface, picking up these rocks. That's what we have on sample here for you today. This is right on the edge of one of those big basins, and the astronauts physically put this into boxes, materials, brought it down back here to Earth, and subsequently we've been studying these samples ever since. In fact, NASA even has samples that aren't open. You might think that we've done it all. No, we have not, folk. There's many mysteries of the moon. The large mountains that you see on the moon are telling of geologic processes that we actually don't fully understand ancient lunar geology. Okay, so I think we can go ahead and take it to our view of the moon. Now, if you know Texas, you know we get some clouds. So we are going to show you what we recorded a few days ago to show you what our telescopes typically get to see. We are a little bit clouded out here at the moment, but we might get some gaps, just to remind you that we're here both in person with the demos and all of the folk checking them out, looking through the telescope when we can. Speak of the moon, it's come through. And so let's go ahead and enter any questions that you might have as we have the view of the moon in there. The terminator is where if we had an atmosphere, but that means there's really no atmosphere to scatter light, just like we see the beautiful red sunsets or sunrises where the longer wavelengths of white light coming from the sun are scattered by particle sizes in our atmosphere. Hey, there's no particles. So that means there's no technical beautiful sunrise color display on the moon, but where that terminator is where that would be. Any side of the moon, pick your favorite side, experiences 14 days of light followed by 14 days of darkness, which becomes our lunar 28 day. And that terminator line is where that material, these are the same size scale mountains that are here on Earth. And as I mentioned briefly a moment ago, there's geology atop of those mountains that we don't actually fully understand. There's comprehensive and elegant the crater walls. And in fact, this is the best time to get a little bit of depth perception on the moon. Here on Earth, things that are closer and further away to us, we have depth perception with. There's only 2 objects in space that we get depth perception with. The moon, when you have the terminator, when you can get those shadows cast by the mountains or the crater edges down into those crater floors, or Saturn. Saturn has a large ring system around it, and due to that equatorial tilt of Saturn, we can get a little bit of depth perception with these 2 objects only. We're going to go ahead and take any of the live audience questions now. So we're checking the chat. Drop in the chat if you have it now. This can be about the moon that you're seeing in the view, or we'll take a closer look at the hollow sample, but you could feel free to ask about that. Moon tree, that's going to be our live stream there. Okay. Oh, I swear this wasn't a seeded question, y'all. This is great. How is the moon formed? Through impact physics. Okay, so we're talking about 4.8 to 4.6 billion years ago. The theory, the leading theory, is that a meteor, an asteroid, okay, a small planet, set off a lot of material off of Earth. And you know, us astronomers, we'd love to name everything. The impactor is named Theia. Theia hit the Earth so hard that Theia and Earth material blasted off in a beautiful display of impact physics. But due to conservation of angular momentum, the nearby material started coalescing. Okay, and what I like to call a sideways snowball effect. One particle grabbed another particle, and slowly the moon formed. Now, if you really want to go a little bit deeper, it's theorized that not only did that impact hit so hard it blasted off materials, but there's geology theory that the impact was so tough on Earth, it started plate tectonics. We're actually not sure how plate tectonics on our planet fully started. A good working theory. Now, not only was there theorized to be the one moon from this big moon impact theory, sideways snowball, but it's thought from Dr. Eric Asfog, one of my favorite mentors, is that two moons formed. And there's a really great public book I encourage you to read called When the Earth Had Two Moons, because we think that the little moon might have smacked into our moon. But that's a working theory. Any interesting moon occurrences happening? Yes, on Tuesday, we'll back out observing with our telescopes here in person on Tuesday 17th. There is a supermoon, and not only that, but a tiny bit of an eclipse. So there's going to be a lunar eclipse, so a little bit of that Earth shadow will be caught on the edge of the moon, while the moon is in its closest part of its orbit. It's like you guys are leading me to my demos, because it turns out that the moon distance in which how it moves around Earth is not fixed. We orbit around a barycenter. That means sometimes as it orbits around a common center, the moon can be a little bit closer and a little bit further. When it's closest, super close, we have a supermoon. Closest approach of a supermoon's coming up on Tuesday. What is my favorite crater? Oh, good question. Shackleton. All right, Shackleton's almost exactly at the South Pole, and that's where the Artemis 3 geologists are putting boots back on the ground, folk, and not only just boots on the ground in human form, but both males and females. So nice representation. Solar system, we think we're a lot bigger. Think about and the big impactors are what hit the moon so hard that hot lava flooded up and infilled the impact basins. It's basalt, y'all. Basalt makes up about 80% of the entire solar system. Even below our feet, the mantle is made of basalt and olivine, which I have here. 86% of the solar system is basalt. Maybe you love it or you hate it. Okay, so now we're gonna fade in for a little bit of a scene change here, because like we said, we got physics here for you. We're gonna show you a few of our favorite physics demos. Enjoy the symphony while we change.
I'm a graduate student in the astronomy department, and here I have our barycentric Earth demo. The moon orbits the Earth. So it's a little hard to understand how celestial bodies move in space because we're so used to electromagnetic forces here on Earth. But out in space, there's not a whole lot of that, and the dominant force is gravity. So you may think that the moon simply orbits around the Earth. But that's not quite the same. As Allison mentioned, there's actually a point somewhere between the two masses, a center of mass that we call a barycenter, and the moon does orbit around the Earth, but at the same time, the Earth orbits around the moon, and they both orbit this barycenter. On the actual Earth, it's about 1,000 miles underneath our crust, but it's always moving around as the Earth and moon move around it. So just to start the analogy, I'm going to give us a little spin here, and then we're going to let it go. And as it spins up, you can start to see that our Earth and our moon start to have a little bit of a wobble as they orbit that center of mass between them. This is a very similar way that the moon moves around the Earth and the Earth moves around the sun and all of the planets. The entire solar system works like this, where gravity is the dominant force in space and everything.
Let's bring another demo in. One moment, folks. Okay, you want to be the person on the chair?
I was voluntold too.
Yeah! Okay, cool. We got one grad and one undergrad. That's perfect. Okay, so it'll be too hard to mic you, so I'll introduce you.
Will you do the talking?
I'll do all the talking. So you just be the demo person. If you want to be the spinner, that way I can focus on talking, or you want to do it? Okay, and then let's get these just a little bit out. So hold it, I'll cue it. I'll cue it all at once. I'll walk you through everything. And this might be a little too close. Let me just do this. Liza? No. Your name? All right, welcome back, folk. So here we have displaying our angular momentum chair, the most important equation of the solar system, the conservation of angular momentum. It's the way in which Earth has a spin from the formation around the sun, how the formation of the moon stole some. Michael, these are undergraduates from our physics and astronomy major here at Texas A&M. This is one of our most popular ordered demos at the Physics Lab Center because this is physics you can feel, y'all. So Michael, go ahead and start in position 1 with our weights. It's all about, go ahead and have your arms nice and far out. So let's start with perfect. Go ahead and give them a kind of boring, right? Go ahead and bring those weights into the center, Michael. Yeah, physics you can feel, physics you can see. So where the mass is matters, right? Let's bring it back out to slow it down, especially if you're getting dizzy. And we can see that the angular momentum is changing, right? Momentum is meaning of moving mass. And so you're made of mass, the weights are made of mass. And when you bring all of the mass into the center, you see the spin rate go up. Spread those arms out, spread out the mass, increase that radius to see the distribution of the mass, slowing down the rate. So let's go ahead and slow you down completely. And let's go ahead and get that wheel going. We got one more trick for y'all, all right? So go ahead and get Michael nice and spun up, So direction of rotation also matters. We're gonna spin it in one particular direction and go ahead and see which way has a dominant way. Okay, let's check the other direction. 180 the other way. Okay, one's a little bit stronger than the other. So the rotating wheel here distributes the, or rather, it can change how the rotating wheel on the bottom is. This is actually how we drive rockets in space. So we use rocket fuel to get things up, and we use moving momentum and reactionary wheels with masses on it to angle in which a spacecraft or a lunar lander might want to land. Just like when we threw the Ranger. It's also what's in your selfie sticks, y'all. If y'all got a selfie at home that's got that gyroscopic, gonna keep your selfie nice and stable through spinning wheels and masses on the inside. All right, let's go ahead and get our demos out of the way. We're happy to also field more questions. Make sure you get them in the chat. Okay, so Lunar View, we've had
as we sail the dark full moon rays
All right, we're back answering some questions from the chat, y'all. Here's a question that I was really hoping would be asked. Why can't we see the other side of the moon? Fantastic. You notice that we have a lunar near side and a lunar far side. Now, you might really enjoy Pink Floyd Dark Side of the Moon, and you should, it's great rock and roll, but there truly is no dark side of the moon constantly. Any spot on the moon experiences 14 days of light followed by 14 days of darkness. This is a lunar day. Now, this magic number is 28. That is the lunar year. This is where a moon year equals a moon day. So what does it resolve to? That means that you are always stuck seeing the same side as Earth because the rotation is such that even though I'm spinning, I am moving around it. Okay, so the moon day equals a moon year, which is about 28 Earth days. This is probably due to the way in which it originally formed around us from that large impact. Another question, if the moon were split in half, would it hit the Earth or would it form two moons maybe again? That's a great question. Every large object in space that has mass has what we call a Roche limit, okay? And the Roche limit is the threshold when you get destroyed. So for instance, that Theia impactor entered the Roche limit and fell down to Earth and impacted us. Now, each different planet has different mass and a gravity field. So the Roche limit is different for each of the objects, celestial objects in space. But the moon doesn't fall in towards us now, right? Its angular momentum conservation keeps it outside of the Roche limit. But if it broke in half and half of it fell in beyond the Roche limit, we'd have a bad day on Earth. Let's see. I think that we can also answer any questions. Apollo sample. And We'll get a closer in view of the live sample as well for y'all. Now, I also want to highlight that we have different glasses. So our impact glass really high temperature events. On the moon, there's no atmosphere, so things cool under the presence of no atmosphere. But you might see volcanic glasses here on Earth that can actually form from volcanic activity. They often will have bubbles in it. Okay, so I have some volcanic glass up here that is kind of see-through. Now that can be a little bit tricky because impact glasses, things that form due to impact, can also be quite glassy looking and in fact are a glass. So if you've ever heard of what's called tektites, tektites are due to a large meteorite impactor hitting Earth, hitting sediments that instantly melt and then cool. Very cooling. If you can see any mineral crystal, that means it cooled very slowly. Anytime you see or can't see a mineral and smooth like a glass of a window pane, there's crystals there, but they're microcrystalline. And this happens when there's cooling very, very rapidly, which occurs during impact physics. Are we getting an okay view of the sample? Can you take a look? Can you see that there's glasses on the outside? Apollo 15 sample right here is a cut of a larger rock. This is 93 grams. This is rock that is representative of much of the lunar surface, what we call regolith. Again, if you know us astronomers, we love to name everything, okay? Lunar regolith is the same flour that you have in your pantry is what the lunar material is made of from pulverizing impact physics, y'all. The moon has experienced so many impact physics over time, it's pulverized the rock to a pretty consistent grain size, although there's variation in there. Now, just like here on Earth, when you have sediments that get compacted and turn into a physical rock that you can hold, this can happen with the lunar regolith as well. So this is a lunar regolith breccia, which is broken up impact pieces that had enough force stress on it to lithify the rock. So here inside of the lucite holder, again, this is our on loan from NASA Apollo 15 sample, is a truly lithified rock that is the pulverized regolith of the surface of the moon. Let's get some more questions. So how do astronauts stay in space without floating away? This is a great question too, because we're putting humans back on the moon. So when the astronauts were able to get to the surface of the moon, there's 1/9 the gravity that the moon has. This is enough gravity. Now, for the International Space Station astronauts, and there's something like 15 astronauts up there in orbit around us right now, all working. Many of the astronauts in there, when they go do a spacewalk, they're tethered. Because if you get out of the moving space station and are tethered to it, you're effectively still with the space station. So the astronauts in orbit around Earth are actually in a constant free fall state. So they are constantly falling towards Earth, but there's thrusters and some motion in the space station that typically keeps it at a relative height. And they're moving at about 7,000 miles per hour. And let's see, how strong is the moon glass? Oh, very good question. There's actually a few different types of lunar glass. Now, there's a very, very special, unique glass that, as I mentioned earlier, there's mysteries of the moon. There are things we don't understand. They're lunar glasses that are orange beads. NASA doesn't really put those out on loan. The lunar orange beads are a mystifying lunar glass. They are generally strong. I don't know the scale of it. We might be able to put the chat later. There are different strengths of rocks that we actually rate them to. That's a great question. I don't know the exact strength of that. But then there also are the darker lunar glasses as well. And arguably the orange lunar glass and the darker glass probably even has some different strengths to it. When I talk about strength of the rock, that's that maybe how rigid it is. Like one of the strongest things here on Earth is diamonds. Oh yeah, don't forget that we're in College Station, y'all. Choo choo! We got a big train moving behind us. That's when you know we're really here. Let's see. Now let's take you to the moon. Let's take you back to our moon view, back to our telescopes. or may not know, we have our moon naming tree competition opened up a few weeks ago from receiving our native to Texas American sweet gum tree. Okay, so we asked the world to name our NASA moon tree. We had a lot of really great submissions from all around the world. We had great judges, and you made it really hard on us, folk. But we had a winner, which was a nod to both the Apollo, the lunar missions, Texas A&M University, and NASA, all coupled into one. The name of the tree is dedicated to Jerry Griffin. The name suggestion is Jerry, and this came in from Mr. Jeffrey Hasley of League City, Texas A&M, and League City, Texas, from Texas A&M University classes 2002 and 2019. Thank you, Mr. Jeffrey Hasley. Thank you to Mr. Jerry, who is the Apollo flight director from Apollo 12, 15, and 17. He was the lead flight director. He was graduating class of 1956. He still gives public lectures. He's very active in the Texas A&M community. We hope to invite him out when we actually put this tree on the ground. We reached out to him. He accepted this great honorary tree in his honor. And he was also the one responsible at the beginning of our live stream. We had our Texas Aggie hymn that he was responsible for broadcasting on the surface of the moon. So the Apollo astronauts got to wake up to our Aggie chant, which was pretty neat and a pretty great thing to do as the Apollo flight director. So well deserved. Some great runner-ups: Luna Cantha, Argonaut Moonbloom, and two different submissions that had a similar name, Daphne and Daphnia. We actually are going to give a nod to these 3/4 runner-ups when Jerry here, who has both male and female components of a flowering tree, will drop descendants. If you're in Texas, y'all know about those impact bombs that these drop, which are the little sucker seeds. Those are going to be moon tree descendants, and we're going to name our first 3 descendants after our first 3 runners up. They were all very great submissions, and our punniest and our funniest that made us laugh, Chabarka. All right, you guys had some great stuff. We've got Jerry here. Jerry's a great name, and we're really excited to get Jerry into the ground. So let's start wrapping this up. We are going to close tonight with kind of how we started, with part of the Moon Symphony. This was composed by Amanda Lee Falkenberg, and each of the songs in the symphony are dedicated to and inspired by different moons of our solar system. And Amanda was able to work with planetary science data and planetary scientists to put this composer together. So we'll go ahead and end it with a little bit of music on the outro. And if I can get an A, woo! All right, y'all, until the next one, we'll see you around.